Hello, my name is Daniel Lemus from Purdue University, and my presentation is about how to preserve the Kramers-Kronig relation in inelastic atomistic quantum transport calculations. To begin, I'll introduce the NEGF formalism, a widely used method for solving the Dyson and Keldysh equations. These represent electronic occupation in atomistic devices. An important part of the NEGF method is the use of self-energies that represent external perturbations in these devices, and this may include electrons entering and exiting the device, and incoherent scattering phenomena such as phonons. An often encountered issue in these simulations is that they're very computationally expensive. In this work, we use a clever mode filtering method detailed in this paper, often called a mode space basis reduction. This mode space method can reduce the rank of the matrices used in the NEGF method down to a single percent of the original matrix rank. And in this example, we reduced the size of matrices having 3,000 rows and columns down to just 100 rows and columns, which will result in a huge reduction in computational complexity in NEGF calculations. Another common method of reducing the computational complexity of expensive equations, like scattering self-energies, is to remove part of the calculation entirely. For example, it is common in simulations that use mode space to entirely remove the real part of the retarded scattering self-energies, or sigma r, which may often result in deviations in physics. But since we can use the mode space basis reductions, we can take advantage of these reductions and solve the sigma r exactly, including the real part. In this work, we solve the imaginary part of sigma r, which is responsible for dephasing of electrons in the device, and we solve the real part of sigma r as well, which is responsible for the shifting of resonant energies. A very important aspect of the real part is that it is in the form of the Kramers-Kronig relations, and can be solved with a Hilbert transform using the imaginary part. And since this needs to be solved for all matrix elements, mode space can reduce the number of Hilbert transform operations down to under 1% of the number of operations needed in a full basis. So to demonstrate this, we simulate an example of an indium arsenide tunnel FET or TFET, and it is solved in atomistic type binding, including 3 types of scattering. We solve a current voltage curve for 3 cases. First is it's without any scattering, just ballistic. The next with scattering, but without the real part of sigma r, and then with the real part of sigma r calculated using the Kramers-Kronig relations. And this is all solved in mode space using our software Nemo 5. So first we show the IV characteristics of a square 2.4 nanometer wide TFET, and the inclusion of scattering with and without the real part of sigma r, as you can see, increases the off current and decreases the on current. Now we show a square 3.6 nanometer wide TFET device where the situation is a little bit different. Like before, the on current is decreased by including scattering without the real part of sigma r, and it's decreased even more with the inclusion of the real part of sigma r. But now we can see that the scattering may not may not simply increase the off current as before. As you can see, the case with the zero real part actually decreases the off current. So can we see the same thing happening while including the real part of sigma r? For that, we increase scattering using a scalar factor in the next slide. So with scattering increased by a scalar factor of 10, there's an even greater decrease in the on current from the inclusion of the real part of sigma r. And we see now that there's also a decrease in the off current even when the non-zero real part of sigma r is included. So the effect of scattering on off current may be situation dependent. Therefore, the real part of the retarded scattering self-energy, sigma r, should be included for an accurate physical representation. To explain the reasoning behind the changes in current due to the inclusion of the real part of the retarded scattering self-energies, we bring up these previous NEMO 5 results shown in IWCN 2019. These previous results, though, did not include mode space like this work does. Here we see the energy resolved conduction band density of states, and we see there is a shift in the density of states due to the inclusion of the real part of sigma r. This shift in resonant energies can cause some unpredictable changes in current and should therefore be accounted for. This exact solution of the retarded scattering self-energies, sigma r in mode space, are available in NEMO 5. All of the features described in this work can be accessed through our software in NEMO 5, of which the latest version can be found licensed by Silvaco through the URL shown below here. Thank you for your time.